Hello everybody, I'm Hyunbin Kim and I'm a PhD candidate student at Tainago Lab from Seoul National University in South Korea. In this video, I'm going to introduce our protein structure compression tool for the comp. As AlphaFold2 produces structure predictions at high quality and speed, EMBL and DeepMind have announced to soon release a database containing over 100 million predicted structures. A future with billions of predictive structures is soon imaginable with this trend. However, with the advances in speed, storing all the structures is becoming a major issue. 1 billion structures would require hundreds of terabytes. So we designed a novel format and method to compress protein structures requiring only 10 kilobytes for a protein structure of average size. We reduced the required storage by an order of magnitude through encoding the torsion angles in a compact format. We could reduce the storage required to 13 bytes per residue, which saves about 84 bytes compared to 3D coordinates. Now I'll continue to explain our compression method. First, from the PDB file, we extract the backbone atoms and group the whole atoms by residue. Next, the torsion angles and the bond angles are calculated from the coordinates of the backbone atoms. Not only the torsion angles, the bond angles are also saved in the compressed file for less deviation from the original coordinates. Torsion angles in the side chain of each residue are also calculated in this step. All the angles are saved in the compressed file after discretization. We encode the angles by binning into a fixed number of bins. For the backbone torsion angles, we use 12 bits for psi and phi angles and 11 bits for omega angles. For the side chain torsion angles and bond angles, 8 bits are used for encoding. In addition to encoded angles, we save more parameters to reconstruct the whole peptide structures, like minimum values, the number of bins, the absolute coordinates of first 3 atoms, the lengths, and also the indexes. The angles and parameters are saved into our novel compression binary file format, FCZ. FCZ format mainly consists of 3 parts: header, backbone, and sidechain. All FCZ files start with the magic number FCMP to indicate that it is a compressed file. Header contains the number of residue atoms and the starting indices of the first atom. The 3D coordinates of first atoms and the factors for discretizing angles of backbone are also saved in the header to reconstruct the whole coordinates. The next part encodes the angle in backbone chain. 20 amino acid type is encoded with 5 bits, and the torsion angles are encoded with about 12 bits. The 1 byte encoded bond angles are saved in the latter part. With this encoding, we could encode the backbone information with only 8 bytes per residue. Sidechain torsion angles are encoded with 8 bits, and the values were concatenated in the last part of the file. On average, 1 amino acid has about 5 sidechain angles, and it makes the total required storage space about 13 bytes per residue. In the decompression part, the encoded angles are restored to the original values. To reconstruct the coordinate, we use natural extension reference frame algorithm, which is called as NURF. NURF is a method to calculate the upcoming atom's coordinates using the coordinates of 3 previous atoms. To calculate the vector to the fourth atoms, it requires the bond angle, bond lengths, and the torsion angles between the bonds. Reconstructed atom coordinates are saved in the decompressed PDB file. We compared FoldComp with 3 other compression tools, gzip, Percra, and PIC. Gzip is the well-known general compression method, and the other tools compared are specific to protein structure compression. Percra uses C-alpha coordinates, and PIC utilizes PNG format to compress the coordinates. When compressing the structures of AlphaFold is the proteome, FoldComp achieved the highest compression ratio of all the compression tools. The average output file size for FordComp is about 10.2 kilobytes, which is 10 times smaller than the original file. The compression and decompression speed of FordComp was the second fastest after gzip. Though PerCra didn't take much time in compression, it was the slowest in the decompression part. However, PIC was faster in the decompression step than our tool, but it took much time in the compression. We measured the loss of algorithm with RMSD between the original structure and the reconstructed structure after decompression. From the result of 5 PDB structures, FordComp achieved best RMSD in 3 cases and second best in 2 cases. In most cases, the RMSD was below 0.5 Armstrong, and which shows that the loss of the algorithm is much less than the experimental error. In conclusion, we developed a fast and efficient protein structure compression algorithm. We published our tool in the GitHub at this link, and it's available for public use. Thank you for your attention.